Welcome back. So far we have seen problems, how to we have seen only how to solve problems, boundary value problems using Fourier transforms. Basically what we have seen is the Fourier transform and its applications in the last component. So we will start, we will define what is called the Laplace transform in this video. So to start with, we will just consider Fourier integral theorem that we have proved earlier videos. So we just take this Fourier integral theorem, start with that Fourier integral theorem. So what is that you have? So what we have is, if I have a function, let us call this f1 of x. Okay. Fourier integral theorem is basically you define a Fourier transform and its inverse transform for an absolutely integrable function. So you consider f1 be such a function, be an absolutely integrable function, where it is defined as its defined function in minus infinity to infinity. So full real line. Okay. So if you are given a full real line function, absolutely integrable function, that is our full real line, what you have is you can break this into this way. So f1x as a positive side. So you call this f1 f11, let us say. Okay. So f11 of x is f1 of x for x positive, and then x this is 0 for x negative. Okay. I break this f1x into two parts, that is f12 of x, this I define if it is 0, if it is x positive, and its negative side what you have is f1 of x when x is negative. So if you want this to be defined for positive side, so what you should have is so in an equivalent way you can write this as 0 if x is negative, okay, 0 if x is negative, and this one here f1 of minus x if x is positive. So this is same as saying this one, f1 is when x is positive, f1 of minus x is it's f1 of negative thing. So that is exactly our function. So this is for x positive and this is for negative side, this is 0. So this is how you can split, so that your f1 of x equal to f11 of x plus f12 of x. So we will consider only one such function. So let us choose only this part. So this part you can do similarly, whatever we can do. Okay. So this is also absolutely integrable if f1 is integrable. If f1 is absolutely integrable, f11 is also absolutely integrable, f12 is also absolutely integrable. So typically f11 is such a function. So f1 we can consider now. So let now we can always do this breakup of the domains, so that you can rewrite f1 as two such functions, where positive side is there, negative side it is 0. So it is only defined positive side. So now I start with this f1 of x as such function. So f1x is actually f11 of x. I choose this typical typical function for x positive, x belongs to 0 to infinity or minus infinity to infinity. Okay. So if I choose this one, only one typical function one I consider. So you can also do the same way for this one. Okay. If I choose this, if f1 is if f11 is since this function f1 is absolutely integrable, so you can see that this let us call this f2. Okay. f2 is this one, f2 is also absolutely integrable, f2 of x is absolutely integrable in minus infinity to infinity. So what do you have from this Fourier integral theorem? This your f2 of x is equal to 1 by 2 pi integral minus infinity to infinity e power or inside you have this Fourier thing. So, that is minus infinity to infinity. So, 1 by root 2 pi, this you have root 2 pi actually. So, this is together is 1 by 2 pi. So, this one into f 2 of x into e power minus I xi x dx, then this is your function of xi and you have e power I xi x dx d xi. So, this is your Fourier integral theorem, this is what you have. Okay. So, just to avoid this x, this dummy variable I will change to t, this is t. So, that you have this is the Fourier integral theorem. This is true as we have seen in the earlier videos because of Fourier integral theorem. So, this is true, always true. So, I will do some now you can put what is your f 2 of a, f 2 of t is f 1 1 of x, f 1 1 is basically f 1 x, f 1 x so let me choose f 1 x. So, what you get is 1 by root 2 pi integral minus infinity to infinity 1 by root 2 pi, this you can put it together as 1 by 2 pi and you have this is from f 2 which is f 1 1, f 1 1 is basically your f 1, f 1 is only x positive side. So, it is from 0 to infinity f 1 of t e power minus I xi t dt times e power I xi x d xi. I just substitute what is f 2. So, if I choose x positive side, I can write what is f 2, f 2 is f 2 of x, x positive side, which is same as f 1 1 x, x positive side, f 1 1 x positive side is f 1 x. So, f 2 is actually nothing but f 1 of x for x positive side. Okay. So, here where f 1 of x is an absolutely integrable function. In minus infinity to infinity. Okay. That is what f 1 x is basically from 0 to infinity, right, in 0 to infinity. So, that is what you have. If you have this is actually comes so far from Fourier integral theorem. Now, I choose some particular function for f 1 of x, which is some function which is not absolutely integrable function, but if I multiply with exponential with some minus c x, okay, this is for x positive side, then f 1 of x is, then once I multiply this for x positive side with e power minus c x and c is positive, if I choose like this is absolutely integrable function. Okay. Or you consider such functions f for which this is this product of e power minus c x with such f such functions f x together, assume that it is absolutely integrable. Okay. So, what how do I write this? Let f of x be such that is this with c positive is an absolutely integrable function, integrable in 0 to infinity. So, such class of functions, for example, so what are such functions? So, for example, you can think of e power a x, okay. So, f x behaves like e power a x at infinity, so that if you multiply with e power minus c x, with a is less than c. If a is less than c, what happens? This is like exponential a minus c. So, what is this one? This is actually equal to e power minus a minus c minus a, because c is bigger than a into x, this is absolutely integrable function. So, from 0 to infinity it is integrable. So, one such function is, so I have to write example means e power a x, f of x is e power a x with a is less than c. Okay. So, this so that you can easily see that this function, this e power minus c x implies e power minus c x times f of x is equal to e power minus c minus a times x is, so that this integrable. So, this is infinity dx, infinity 0 to infinity dx is actually finite. Okay. You can easily integrate because this is positive quantity, e power negative minus of some positive quantity into x. So, that is what you see. So, because that means it is absolutely integrable function. So, such a class of functions if you consider, now substitute f1 in the place of f1 in this Fourier integral theorem, you substitute this c e power minus cx into fx. Okay. So, if I substitute e power minus cx into fx, which is equal to, so 1 by 2 pi integral minus infinity to infinity, and what you have. So, integral 0 to infinity, and what you have is f1 of t, that is e power minus ct times f of t e power minus I xi t dt times e power I xi x, right. So, I xi x d xi. This is what if I substitute this from this. Okay. So, where is this valid? X positive side. So, you take this, this implies you can rewrite this as fx, take this exponential to the other side to see that minus infinity to infinity e power minus c t minus x. Okay. So, I bring this to the other side, f of t, of course, you have 0 to infinity f of t e power minus I xi t dt into e power I xi x dx, sorry, d xi for x positive. So, this is what you have. So, instead of writing it here, so what you do is, so let me put this e power minus ct, you write, you put it here, this is the integral inside, and you have, when you bring it this side, you have e power cx. So, if you rewrite this as, let me write it properly, minus infinity to infinity integral 0 to infinity e power minus ct f of t into e power minus I xi t so this you can combine with this thing. So, e power I xi I t you take it out. So, if you take it out I xi, or you take it, so f of t, you can write this as f of t times this one and this one, you can put it together and write e power minus t is common, and you can write c plus I xi into dt, this for dt, and you have e power I xi x d xi x positive. So, this is exactly your f of x, which is e power c x times. So, what I do now here is I use c, a new variable c plus I xi. C is a constant, which is, you have seen c is some positive constant. Okay, that is how I started. If I do this c plus I g, you take it as some variable s, let me use some s. Okay. if I use S, then what happens to if I use this one, d xi I d xi will be ds. Okay. So, what happens to this, f of x will be equal to e power c x divided by 2 pi integral minus infinity infinity. So, inside it will become, this is like integrand for you. So, you have f of t e power minus t s dt. So, this is integrand if I use this variable, and e power I x times xi I replace with s minus c divided by I. Okay. Then what is d xi? D xi is ds by I. So, this is what I have. So, you have this I goes e power minus c x and e power plus c x, that will go, and then what you end up is 1 by this I comes out, you have 2 pi I this integral, and you see when you substitute this when you put xi equal to minus infinity, you should write this as c minus I infinity to this c plus I infinity. So, you have c minus I infinity to c plus I infinity, and this integral inside what you have is the same f of t e power minus t s dt times what you are left with is e power x s ds. Okay. This is your f of x positive side. So, this is, I have not done anything, I have not created anything so far, everything I have used only Fourier integral theorem, that is this one. This is the Fourier integral theorem I used, or this, okay. Fourier integral theorem I used, and I only in the place of absolutely integrable function, I choose in this form, my absolutely integrable form function I have chosen in this form. So, that f is such a class of functions, they are for example, one example of such a function is exponential functions are also involved. You can also involve constant functions. You see that constant function is not absolutely integrable function, implies you cannot define Fourier transform on it, but here you can define. So, Laplace transform on it, that is what you will see. Now, you have some kind of integrable Fourier integral theorem for such class of functions f. So, now I can define, like in the Fourier transform, I can define what is a Laplace transform. Laplace transform a script L of f of t, which is a function of s, or we can write f bar of s. Okay. F bar if you put, that is a notation which is function of s, f is a function of t, and when you apply the bar it becomes function of s, which is definition is, I put the semicolon equal. Okay. Assignment state assignment, this is you take this as your definition of your Fourier transform, of your Laplace transform, f of t times e power minus t s dt. What is s? S is c plus I xi. So, what is c plus I xi? If your f is type e power a x, if this is called exponential order function of exponential order e power a x, then your s is basically, I can say is actually s is a real, s is a complex number now. So, s is a complex number, real part of s is actually c. Okay. That c is actually bigger than if if your function is exponential function of order a, for example like this, then it is greater than a, otherwise it is anyway. So, you can think of 0, you can take it as 0 as of now. If your f is a exponential function of order a, then you can put it as a more than a. Okay. So, at the moment let me write real part of s is positive, so that this integral makes sense, is well defined. So, this is your Laplace transform. Okay. So, definition of Laplace transform. So, inverse transform is inversion of inverse Laplace transform. So, what is this inverse Laplace transform? That comes from, like earlier, from the integral theorem. Now, this is your integral theorem. You can write your Laplace transform instead of f of x, let me use f of t. So, if I use f of t, so that is the inverse Laplace transform of f bar of s, which is f of t. Now, in the place of x, if you put f of t 1 by 2 pi I. So, definition is from this integral theorem, this is the definition of a Laplace transform, then the inversion will be this integral c minus I infinity to c plus I infinity, and then you have f bar of s and e power st ds, because it is a function of t. Okay. And that is it. So, you have c is, what is c? So, if your function is absolute if it is a constant function, a is 0, c is always bigger than 0. So, let me put it, minimum c is positive, that way c is simply positive. So, what is this integral? Inversion. In the inversion, integral is a contour integration. So, if this is your x and y axis, so if you take this as your c, x equal to c, and this on this line, your integral is over on this line. So, c minus infinity to c plus infinity. Okay. Because s is always real part of s is positive. So, you can it is defined positive side. Okay. So, here it is well defined because c is positive. So, over which you have, if you for this function f of s, f bar of s times e power st, this is your integrand, integral of this over this line, that is complex integral. So, that is what exactly you have to evaluate if you want to find the inverse, that is you can use your contour integration technique to evaluate this inversion. Okay. That we will see later on. So, this is your inverse Laplace transform. Okay. So, again let me use if your function f is simply if your function f of x is let us say a equal to 0 is a constant, which is absolutely integrable, which is not absolutely integrable function, but f of x into e power minus cx, where c is positive, okay, is absolutely integrable function, then you have this, okay, c is positive. Okay. So, this is then you have same thing. So, you have this Fourier Laplace transform and its inverse transform. Okay. What I have done here is, for this function f, we have this exponential function of order a. This is the exponential function of order a, this one, f of x equal to e power ax is called functions of exponential order, or f of x equal to 1 if you choose constant function or any constant function c or k, then this is a exponential function of order 0, because k times e power 0 x you can write. Okay. So, this into any e power minus cx is absolutely integrable. So, in that sense we can define, we actually consider f means f is all such f of all such functions for which you have this you can define this Fourier Laplace transform and its inverse transform. So, what are those functions? Let me define formally. They are called functions of exponential order. So, I will define what exactly they mean. If f of x is x positive side such that modulus of f of x times e power minus ax, if you take this one, if this is bounded with some constant k as x goes to infinity. Okay. If this is bounded as x goes to infinity, then what is this f of x? F of x is called a function of exponential order a, or exponential function of order a. Okay, this is called the function of exponential order a. So, what does it mean? Is f x is behaving like e power a x, that is f x behaves like big O of e power a x, that is. So, what exactly this means? This means equivalently what you have is f x times e power a x, this limit if you multiply as x goes to infinity minus a x, okay, divide. So, f of x divided by e power a x, that is f of x into e power minus a x as x goes to infinity. This is actually because of big O, this is a big constant that we call it k, okay, such that for k positive, for a positive k, then this is called exponential order, function of exponential order. So, that is actually, this is the meaning of this. That means f x behaves like order of big O of e power a x. Okay. So, if your function is exponential of exponential order a, then you have this is true. Okay. But now if you use this your earlier definition, so if f of x equal to, or rather if e power minus c x times f of x is absolutely integrable, means, then what is the meaning of this? E power minus c x into f of x, this goes to 0 as x goes to infinity, that is the meaning. Okay. It is not constant, it is 0. So, that means f of x, what does it mean? F of x behaves like order of rather order of e power a x, okay, where a is less than c, right. That is the meaning, right. So, what does it mean? F of x divided by e power a x, e power minus a x, okay. Okay. So, this divided by this, what does it mean? If this behaves like e power a x as x goes to 0, x goes to infinity, this has to be constant. Okay. So, how do I convince you that this means this where a is less than c. If a equal to c, then this has to be constant, non-zero constant, okay, but that is not the case, it is going to 0. That means, so if this is the case, f of x is some constant times e power c x, okay. So, if my f of x is like constant times a is less than c, then f of x into e power minus a x, okay, this limit x goes to infinity is actually equal to k, which is positive as x goes to infinity. Okay. If a equal to c is actually what you have, if a equal to c, then k into if a equal to c, e power minus c x into a k times e power c x, that is going to be constant, but that is not true. So, what you have is if you multiply like that by taking k f of x as k times e power cx, then it is converges to the positive constant, but that is not true, it is actually going to 0. That means f of x has to be like this with a less than c. Okay. So if you have, what we have used is if you use this e power minus cx f x is absolutely integrable, then this goes to 0 as x goes to infinity. That means f of x is an exponential of function of exponential of order a, where a is less than c, that is the meaning. Okay. A is less than c, this is the argument with which you can see that the moment you see if it is going to 0 and this function is exponential of order a is less than c, that means it is of exponential order it is like e power ax, a is less than c. So that if you go back, if you look at here, so what happens here? So what is your c or what is your s? Real part of s is, so if you look at the Laplace transform now with this definition. So once you know this, it is a function of absolute, it is an exponential function of order a which is less than c, then what is your Laplace transform? F bar of s which is equal to 0 to infinity f of t, this is the definition, okay, e power minus st dt. So what is your s? S is, s you have seen is c plus I xi, right, that is exactly what you have, right. Earlier what is your variable? S, we have introduced a variable, s is where did we use that s? S is c plus I xi. So c plus I xi, xi is between 0 to minus infinity infinity. So c plus I xi, okay. So real part of s is actually real part of c, okay, that is real part of s is c, because we have seen that if I choose f x into e power minus cx goes to 0 as x goes to infinity, f x is of exponential of order a is less than c. So you have c is bigger than a, right. So that means if, now I can write definition, if f of x is an exponential function of order a, then exponential of order, then if that definitions are if your Fourier Laplace transform and its inverse transform, if they have to be valid, a has to be less than c, that is what it means, because order a has to be less than c, then only this is true, because s is equal to c plus I xi. So that means real part of s is c which is a. So put it together, we can remove and write real part of s is greater than a, okay. So that is the meaning, which is anyway, so a which is positive, which we know because it is exponential of order a which is positive, okay. There is nothing like exponential of order negative order, okay, only positive order. So with that definition you have this for a Laplace transform, and your inverse transform is 1 by 2 pi I c minus, this is now your c. What is your c? C is, let me write c is I infinity, c plus I infinity times f bar of s e power st ds, okay. So this is your inverse transform. What happens your c? C is in such a way that c is actually greater than a. So real part of s, again what is c? Real part of s which is c, c. So that is actually s is actually real part, so that is c is bigger than a. If your function is of exponential of order a, your c, what you have to consider is, if you are the moment you have an exponential function of order a is positive, here a is here, you have to choose, you can choose any c which is beyond, which is bigger than a, that is your contour integration over this. anything you can choose here also anything you can choose as which is bigger than A, that is all. That is the meaning of inverse transform. So, inverse transform you have this by the integral theorem, but then you have to see that understand that C is actually bigger than A. That means anything, any line from that is C, any line C either here or here. So, you have C plus minus I infinity to C plus I infinity. So, over which if you integrate this integrand, that is exactly it will give you back your function f of t. Okay. That is the meaning of this. So, you have extended the class of functions. Initially Fourier transform and inverse transform is defined only for or rather Fourier integral theorem is defined only on absolutely integrable functions. Those class of functions you extended to now and you define the Laplace transform and its inverse transform. That means Fourier integral theorem we modified in such a way that modified Fourier integral theorem is now valid for functions that are extended class of absolutely integrable functions. That means other than absolutely integrable functions you also have constant functions, exponential functions of exponential order is some any A, okay, any function, any exponential function of order A, for example, okay, all these exponential. So, you have extended all absolutely integrable functions are of order exponential functions of order 0, okay. So, here these are also and this definition once you modify the Fourier integral theorem, these definitions later on then you define this Laplace transform and inverse transform for functions not just for absolutely integrable functions, but also for extended class, that is exponential functions of order any order, okay. So, if you have a finite order or exponential function of finite order, you can define this Laplace transform and inverse transform. So, that is the meaning, okay. So, what you have is finally if you look at this Fourier integral theorem, modified Fourier integral theorem, that is this, okay. So, where is this is what it is, Fourier integral theorem. If you modified your Fourier integral theorem, this is exactly what you have. This is the modified Fourier integral theorem, modified Fourier integral theorem. Now, it is valid not just for integrable functions, absolutely integrable functions fx, but also for any functions, constant functions, exponential functions of order, some order, okay. So, all these, so you basically extended the class of definition of f. So, the domain of this integral theorem, so for all functions, these functions which are valid here, that class you extend it to bigger class. So, that you can define what from that Fourier integral modified Fourier integral theorem you have Laplace transform and its inverse transform. And what kind of functions you have? So, these are bigger class, not just exponential functions, not just absolutely integrable functions, but also exponential functions of order A, let us say, okay. So, if any finite order, if you think exponential functions of finite order, you can have this Fourier Laplace transform and its inverse transform. So, what we have done so far is just considered Fourier integral theorem, which we have proved rigorously for absolutely integrable functions, and then we modified it so that when you modify these functions fx has to be exponential functions of order A, where A is less than C, okay. That's all. That's what exactly you have done. That implies if you choose any such functions of exponential order A, then you can define a Laplace transform and its inverse transform. Laplace transform once you define the real part, that S is if you look at S is what is S? S is actually in your inverse transform, if you look at it, the S is basically from C minus I infinity to C plus I infinity. What is that C? C has to be bigger than A, that is C is real part of S. So, here both the cases real part of S is bigger than A is positive, okay. This is how we define a Laplace transform and inverse Laplace transform naturally, but you still do not know, you may have to evaluate, you can evaluate this Laplace transform, but it is not easy straightforward to evaluate this inverse transform for a given f bar of s. Okay. You may have to evaluate this contour integration. So, we will see basic elementary functions, exponential functions, constant functions, all these things. Let us first define, let us calculate what is Fourier Laplace transform, and then you can, once you know its Laplace transform, because you started with the function, we already know inverse transform is the function itself. Okay. So, that way we will just try to gather the elementary functions for which you know Laplace transform and inverse transform. So, you can have them in the mind. Okay. And then eventually we will see the properties of this Laplace transform, and then we will see its applications later on in the later videos. Okay. So, we will see next video, we will start making evaluating Laplace transform for elementary functions. Thank you very much.